All right, good morning. How is everybody doing today? I have no sound. All right, good morning. How's everybody doing today? Good, good. Good and cold. Let's see if I can get my sound working. All right, I think I'm on the air. Cool. I am not. Now I am. All right, I'm here. Yeah, that was me looking at my email inbox. No. All right, cool. So this is week 10. We are almost done with the course, amazingly. Yeah, that's a good question. So we have class today and tomorrow, and that's it for the week. And then next week we have 5 days of class, and that's the end of the quarter. So coming up to the end quickly. So we're done with programming assignments. I am not going to give you any more ODPs for this quarter. We'll start up with ODPs for 222 in winter. But so technically, all of your programming work for this course is done at this point. I eyeballed homework 8, and hopefully you turned it in, but the usual 20% of submissions are missing, so hopefully that's not you. But I'll grade what I have and post comments. I will not get it graded in the next day or two. It's probably going to be over the break before I get to it. So be patient. And if you did not turn it in, or if you're not positive that you turned it in, I'm going to make a really good suggestion to you. Do not mess with your Git repository, okay? If I get to your assignment and I know that you've been working on this, but I can't download it, you didn't make me a report or something like that, right? I may give you the option to go ahead and submit it late. But when you do that, if the repository was created, tomorrow afternoon or something like that, I have no way to validate when the work was actually done. So if you're, leave your Git repo intact. Don't delete it and just recreate it from scratch for kicks until you've got a grade on homework 8. And this is in general, right, for any course you're taking where you're using Git to submit stuff. Always try to keep your repository intact so that you can prove when work was done. That's a valuable record. Interesting. Okay, cool. Yeah, we'll do ODPs in winter and possibly a few of them in spring for Java also. So you'll have more chance to work out your automated ODPer. So any lingering questions on homework 8? Yeah, so there was a little bit of discussion in Discord just now about associative arrays. Um, so associative arrays are actually the most efficient way that you can store and retrieve data. They have a theoretical performance of order 1. We'll talk about order of complexity in winter term, but basically it's a measure of how does your time to do a task increase as the size of the problem increases. And if you have a linear process, like let's say you want to search for something inside a list, right? The most direct way is just start with the first thing, see if that's what you're looking for, check the second thing, check the third thing. If you have 10 things, it's going to take you 10 operations. If you have 20 things, that will take you 20 operations. If you have 50 things, that'll take you 50 operations. So the amount of time changes linearly with the size of the data, and we say this is order n. And that's not a bad performance metric. There's problems where the amount of time increases as the square of the amount of data. For example, a bubble sort. If you have 10 items to sort, you have to do 10 passes on your outer loop and 10 passes on your inner, that's 100. If you have 20 items to sort, you do 20 outer passes, 20 inner, that's 400. So that's an order n squared. And that's pretty bad performance. It means if you go from 1,000 to 1 billion pieces of data, the time it takes your algorithm increases by 1 trillion, right? 12 orders of magnitude, which is horrifying. And there's a lot of algorithms that'll work as log n. That's playing high-low, right? That's a binary search. There's a lot that work as n log n, which is a little worse than log n, but not as bad as n squared. Associative arrays, hashes, have a theoretical performance of order 1. Doesn't matter how much data you have in the array, you can add a piece of data or retrieve a piece of data in a fixed amount of time. Right? That's a theoretical limit. It obviously doesn't work that way in practice, but theoretically, it's a fixed number of operations you do to find a piece of data and pull it out of that array, whether you have 10 things in there or 10 trillion things in there. Okay, that's the power of using a hash. Now, the long execution time on bash is probably not coming from the associative array part. It's coming from the fact that it's bash. It's interpretive. It's going through and it's executing your instructions one at a time. And when you have, thousands of lines of input and you're breaking those into tens of thousands of phrases, it's a lot of looping, a lot of reading your code and processing it. So if you came up with a faster solution by catting and using unique and things like that, you're getting the speed payoff because you're running compiled code, right? Unique is a compiled C program that runs really fast. Sort is a compiled C program that runs really fast, right? And if we coded an associative array in C to do the same problem, it would run even faster than what you get by using unique and commands like that. So even though Wuthering Heights takes 4 or 5 minutes to process using this approach, I don't want you to come away with the impression that you should avoid associative arrays. They really are extremely efficient, at least in theory. And we'll loop back on these in we'll touch on them in 222. We'll use them in 223 for some programming exercises, and we'll see how they can make life good. So yeah, I saw lots of interesting approaches to homework 8, most of which did not follow what we did in class. So that's cool. It's good to see people figuring things out and doing things their own way. So I'll be interested to go through and see how these scripts work. But looks like good work so far. Good commenting that I'm seeing. Good indenting, things like that. And I did a few trial tests, and they were looking like they worked pretty well. So sometime over the next few days, middle of the week, I should get this graded and posted in Canvas. Cool. Any other questions, comments about Bash, associative arrays, homework age, life, the universe, and everything else. It is pretty neat. It's cool after spending so much time dealing with integer indexes on arrays that start from 0. I think it's kind of cool to open that up to something very different, like indexing with, you know, a set of characters or a word or a sentence, right? Yeah, 42. All right, so I want to talk more about nice, yeah, yeah. This whole key value pair thing is very common, and you do find it in APIs. When you make a request string to send out, you usually specify a key and either put a value with it to set something or ask for a value to come back from it to interrogate the state of the system. So yeah, that's cool. All right, so let's talk more about processes. So this will take us through the next 2 days. And this is stuff that I don't want you to, you know, just like tune out and ignore this, but this is not going to be like, you know, a central theme on say the final exam. Okay? What we're talking about here is stuff that's kind of high powered and stuff that you'll definitely encounter, you know, in other courses. But I want to kind of give you, you know, what may be an initial overview of some of these concepts. And you know, we're working in Linux, we're writing C programs, we're going to be doing this for the rest of the year, the rest of the academic year. It's kind of nice to know sort of where some of this stuff comes from. So, I don't know why I'm calling these M1. So there's this command called system, and we can basically say system and put in a command that we could normally pass to the Unix shell, and this will execute that command for us. Right, so right, here's my M1. I forgot to include a library, but if I run this, it shows me what my current working directory is. Right, so it's executing that command. System, so I need standard lib. System returns an exit status basically for the command. So there's various error cases that can occur, right? If there's no shell available, if there's no processes available, if the command doesn't execute, and so on and so forth. But mostly it returns the exit status of the command you execute. So let's print that out. Right? So it executes PWD, and then it shows us the status, which is a 0. If we give it a command which doesn't exist, it gives us an exit status of 32,512, which is kind of bizarre. But this is actually 127 as a byte followed by 0 as a byte. So you can break these exit codes apart, but this exit status actually has two pieces to it. One telling you the result of the command that was executed, and one telling you the result of the call to system. And if a command can't be run, for example, then you get this 127 in the upper byte saying that it couldn't be executed. So let's do a ps-lf. And I think we looked at this on Friday. It was either this class or the other section. When we do a PS through the system call, what do we see? We see our interactive bash shell, which created a process that's running M1, which happened when I typed M1 right here. And M1 created a new process to execute the command sh-c ps-lf. So that system paren call in C is creating a process, having that process execute the sh command, which is a shell, with a switch-c, which says I want you to run the following command, and then the command that we specified. And then that shell, that program sh, created a new process to execute the actual command ps-lf. So all this happens in exchange for just saying system double quote whatever. So let's say cat ha 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 ha. Right, and I run that, I get a stat of 256. Okay, that's an error message related to the fact that there was no such file, ha ha ha. Whereas if I say cat m1.c, right, I run it and it shows me the contents of this program, and then it shows me a status of 0 because it executed this cat command successfully. What do you think this will do? Could be an error message. Although M1 should exist because I'm executing it, so it should be able to delete it. It should get rid of M1. You think it'll print anything? Let's make it harder. So let's try this. So that worked. It did the remove command. It came back with a status of 0, which means success. But it continued running. But now if I try to run it again, it's going to say command not found because it deleted it. So even though we deleted the file M1, it was already loaded into memory and was already executing. And so losing that executable file didn't cause any problems. But if that file was really big and not all of it had been loaded into memory, we could get into problems. If we got to a different part of the program that it needed to read from the file, it might discover the file's not there anymore, and that could freak it out a little. So that's fun stuff to play with. All right, so this is a really straightforward way to execute Unix commands. And you know, you can use this to annoy your teacher while they're grading your assignment, but I'd rather you didn't. So that when you run your program, you have to sit through the steam locomotive, right? But if you want to do that, right, it's just a call to system. All right, or if the person types in the wrong password or something, you know, you can show them the steam locomotive. All right, but there's limitations to this. If you just want to execute a command, that works great. If you want to execute a command and see the output on the display, or whatever standard out happens to be, that works great too. But if you want to interact with a command, this doesn't allow you to do so. So for example, let's just run the BC command. Right? So BC lets you just do calculations. And if I run M1, it drops me into BC. BC is executing. 2 plus 2 is 4. 2 times 8 is 16. Right? But when I'm done, all that my C program knows is the system command succeeded in executing. It returned a status of 0. So if I wanted to use BC from a C program to do calculations, for example, there's no way to do that with system. And yeah, system is in standard lib, and it's standard on Linux systems. All right, so this lets us execute something if we want to use standard in, standard out in the usual way. But if we wanted to do a calculation from my C program using BC, which would be a silly thing to do, right? But if we wanted to do that, or I wanted to use sed, you know, to do some string processing for me or something like that, there's no way to do that with system, because system just reads from standard in, writes to standard out. So we want to look at ways that we can run commands but actually interact with them from our C code. So my goal is to be able to write a C program which will do something like, you know, ask a user for a number and then use BC to calculate 2 to that number. Alright, because BC is nice, right? I can say, I don't know how to do exponents. Do I? Yeah, I can say 2 raised to some big number, oh, but not too big. Right, and it'll show me the result. And I can't do this in C, right? If I pass this to the POW function or something like that, I'll get you know, a meaningless result. So I want to somehow coerce BC into doing work for my C program. So that's what we're heading towards. All right, and we're going to be able to do this through a command called popen. Alright, so popen is a pipe connected way to create a process. It's almost like system. We call popen and we give the name of a command. But when it executes this command, it gives us access to standard in or standard out on this command. Alright, so before we can do this, we have to talk about file I/O. And you've done this in 121, but I want to refresh our memories on this. So fopen, fclose, fprintf, fgets, and fflush. All right, these are our objects of concern. So let's write some code. So let's open a file. So when we want to interact with files, first thing we have to do is open a channel to that file. So we use the command fopen, and fopen takes two arguments. The first argument is the name of the file that we want to interact with, so of course I'll call it haha. And then the second argument is a string that says, do we want to read from the file, write to the file, append to the file, or what? So I'm going to open a file for reading. All right. So this will try to open a file that should already exist called haha for reading. But just opening a file doesn't make any sense, right? It's like calling up a friend and saying, can you open a can of tuna? Well, they open the can of tuna, that doesn't let you make a tuna sandwich, right? You have to have access to the stuff inside the thing that was opened. So we have to save the return value from fopen in a variable, and this variable has to be a pointer to a type of variable called file. So this is going to be fp equals or you could just get a can with a tuna sandwich inside, and then it would be like recursive tuna, which should be a band name from the 80s. So fp equals fopen, right? And this can be whatever you want to call it, but typically it's called fp for file pointer. But it's just a variable that's going to hold information that will let us access the contents of this file. All right, so fp is what we call an input stream. So we can use fp to read from the file. So let's do our famous fgets. Let's read a temporary array that's 120 characters long, but instead of saying standard in, which is our normal input stream, we just say fp. And let's print that out. All right, so this is the same old fgets that we normally have. You live on recursive tuna street. That's awesome. This is the plain old fgets we've been using. Why is it 119 characters instead of 120? Not exactly because of the new line. Because even if there's no new line inside, it'll still only read 119 characters. Yeah, so it's the null terminator. Because it's always got to make sure that the thing it returns to you is a valid string in the C sense of a string. So it can ingest 119 characters and then lob a null terminator on the end. All right, so let's just run this code, and let's take a look at the value of fp. So this is a general comment here, right? It's helpful to put debug statements into your code to see what's going on, but it's even more helpful if you make those meaningful, right? If you take the time to say something like, you know, after calling fopen, fp equals this, instead of just printing fd with a %d, because if you do that, you get a whole bunch of print statements, and you have to go through and say, okay, this fifth output was weird. What was my fifth output? And now you're potentially debugging your debug statements, right? Because maybe you forgot to put a new line after one of your outputs, and so it's really the sixth line of output, right? So be clear if you're putting in stuff to help you debug your code, be explicit about it, right? So that's just a general thing to keep in mind. All right, so we're going to call fopen. We're going to print out the value of fp, and then we're going to call fgets. We're going to print out the string that's returned from that. And I've got all kinds of errors because file pointers are pointers to files, and I'm printing it out as a %d. But I don't care about that because it's Monday. All right, so let's go ahead and run this. All right, good old seg fault. But we did get one piece of information which said after calling fopen, fp equals 0. Okay, let's take a look at fopen and come down to the bottom of any of these manual pages. There's a section on return values. Upon successful completion, these return a file pointer, otherwise null is returned. Okay, null is 0 in 2020 Linux, right? So that 0 is saying an error occurred. And errno is set to indicate the error. All right, we haven't talked about errno yet. We may talk about that next quarter. But basically, when errors occur, there's this global variable that's given a value to tell you what the error is, and there's methods, functions that you can call that will translate this error number into something human readable for you, and will say something like no such file found, right? Because in this case, there's nothing in my directory called haha, and we were trying to open haha for reading. All right, so let's make a file haha. I don't have to fix my typos, but I guess I do. All right, so there's my haha file. Let's rerun F1. Guess what? So after calling fopen, fp equals negative number in the approximate billion range. That's probably a memory address, which is good because it's supposed to be a pointer. And temp was equal to, this is the first line of my file, followed by a null terminator. So this does what we were hoping it would do, right? It opened the file for reading, and then this read a line of input. All right, so let's read. Let's read multiple lines. Alright, so I'm going to call fgets. And remember, fgets return value returns null when the end of the file occurs. So that's how we can detect end of file. So I'm going to do fgets, and I'm going to look at the return value and say, well, that's not equal to null, and we'll print out the line from the file. So we'll run that. There's the 3 lines of the file, and we're done. And our file pointer was a different value. It was a positive number this time. But it's still non-zero, and that's the key. That's how we know that there was no error that occurred. And you know, if we only read 10 lines at a time from our file, it reads in this space is space T. That's the 9 characters, and then it throws an null terminator on the end. And then the next call to fgets starts from the H, goes out through the space. The next call goes through this, and so on. And the last call from that first line in the file gets the new line tacked onto the end, right? And so each time we call fgets, it pulls in another line. All right, so this is you know, largely review, presumably. Basically, fopen opens the file, fgets reads from it, and then ideally we want to close our file at the end. Now, if you don't close your file, when you exit, the file gets closed anyway. But we want to be clean about this. So let's go ahead and close it. And let me get rid of this print statement so we can compile without errors or warnings. Alright, so let's look at creating a file. So suppose we open a file with a W. So now we're creating an output stream. And we'll go ahead and we'll look at FP also. And now I want to write into that file. Well, we can use fprint. Right? And fprint works just like printf, except you have to specify a stream to write into. So printf writes to standard out, fprintf writes to whatever stream we specify in the beginning here. So if we say fprintf, fp, comma, etc., it should write to that file. Alright, so let's go ahead and run this. Alright, so we'll run F3. So called fopen, our file pointer was something non-zero, and then it exited. Did it do anything? Well, my file, haha, just got written, 1039, that's right now, and it is 6 bytes long. And it says 2 plus 2 equals 4, new line. Alright, so this is all you need to do to write to a file. So what happens if we don't close that file? We'll print out hello and then we'll sleep for 60 seconds. And we'll run this in the background. So it's called FP, it's written to our file, but our file size is 0. And if I look at haha, it has nothing in it. And if I kill this program, haha is empty. So we're writing to the file right here, and then we're sleeping. So let me put a print message in here. I'll say done writing to the file. I'll go ahead and run F3. It's done writing to the file, but that file is still empty. Alright, so this is something we call buffered output. General concept here. Let's say we have a C program, could be a bash script, could be anything else, and it's generating output. and it's trying to write something to standard out or to a file or to, you know, some other stream. When you say printf, fprintf, echo, things like that, your output does not go directly to the final destination. It kind of goes into like a pipeline. This is something we call a buffer. It's part of the operating system. And the purpose of the buffer is, imagine writing a file on disk, right? So you have a physical medium. I mean, flash is physical, but you have a spinning magnetic platter, right? And it's spinning 7,200 RPM, so 120 times per second. And you want to write to a file, and that file is located in this section of the disk, right? So a certain distance in from the outside, and it's in this what's called a sector, and it's located between that spot and that spot. And you want to write, you know, hello there to that spot on your disk, right? You have to take this magnetic head, this read-write head, and send commands to a motor that will drive a gear which will move this head in until it's sitting, you know, the proper distance from the outside to be in line with the track where this piece of the file is. And then while the read-write head is sitting here, you have to wait until this disk spins so that this section that you want to write to is sitting right underneath the read-write head. And now you start pumping out bits, chunk, 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 to write your message into the file. That takes a lot of time. Okay, moving that read-write head is an expensive operation. Yeah, this is physics, totally. That's an expensive operation. I won't go Gothard on you here, but or worse, John Madden. But you know that read-write head has mass and it's sitting at rest, and you need to move it, so you're accelerating it, right? And that takes time to get it up to speed and move it to that location. And then, you know, worst case, 120th of a second, if when you're in position, the thing that you wanted to read is over here, you gotta wait for the disk to spin all the way around again. So what's 120th of a second? That's about 80 milliseconds. That's 80,000 microseconds. That's 80 million nanoseconds. If you have a 3 gigahertz CPU, that's 240 million instructions you could have been doing while you were waiting for that head to get positioned on top of your disk. So disk I/O is real slow, okay? And it's not a whole lot better with flash memory either. Even main memory access is slow. So imagine that you're running your program and it says let's write hello into this file. And the next line says, you know, let's write something else. And maybe this is, you know, a C version of Homework 8, and you got 5,000 lines you want to write into your file. And every time that you want to write one of those lines, or worse, one character, you have to go through all this latency. Okay? So all of this output is buffered. When you actually do a printf or an fprintf or an echo, your characters go into memory. And they sit in here until there's a whole bunch of stuff stored in here, enough stuff to make it worthwhile to actually go ahead and write to the physical disk. So you output your stuff, it gets saved in this chunk of memory, and then when there's sufficient stuff, it all gets pumped out to the disk. Okay, so that's buffered I/O. Well, there's other things that will cause this to go out to the disk, and one of those is closing your file. So if you execute an fclose, that immediately writes the contents of your buffer out to the disk. You can also do an F flush. And that says force this buffer, this pipeline, to get flushed out to disk. And by simply doing an F flush, right, as soon as it says it's done writing the file and it's done flushing, I'm guaranteed my data has been written to the actual disk. All right, so this will come into play a little bit, this idea of buffering output, when we talk about processes. It'll come in a lot next year when we start doing networking, because the network stuff is definitely buffered, right? You don't want to send, you know, one character across the network. If you're trying to send a gigabyte file, you don't want to do it one character at a time, because for every character you send, there's, you know, hundreds of bytes of overhead. So stuff gets buffered. All right, so fopen opens a stream, fgets reads from a stream, fprintf writes to a stream, fclose closes the stream and frees up the resources, and fflush we can use if we want to force the buffered output into the file without closing the file yet. Okay. The other thing is, sometimes writing a new line will force your output to get sent. So even if we take out this F flush, and I don't know if this will work or not, but we'll see. So done writing to the file, yeah, that does not work. But if you're writing the standard out and you have a new line, that will actually force the output to appear on standard out. So writing a new line to standard out when it's your screen or something interactive also does an F flush, but not to a file. And of course, if I just let this time out, well, let's do this. Right, so my file's empty. But eventually my 6-second sleep runs out, and now my file has stuff in it. All right, so I'll copy those files over to the shared code area on the server. We haven't put stuff in there in a while. But just if you don't remember file IO, we'll go ahead and leave that up there for you to look at. All right, so what we'll do with this tomorrow is we'll look at popen, which is almost exactly like fopen, except instead of opening a file, it opens a process, right? It creates a process to run a command, and it connects us to either standard in or standard out from that process. And we can do a popen with a read, and whatever output that command generates, we can read by using fgets. Or we can do a popen with a write, and whatever we fprintf into that stream will go into standard in of that command. And so now we can execute commands and look at either their input or output. All right, so that's where we're going to go with this tomorrow, and then we'll start looking at how we do bidirectional communication, and that's going to get us into the super low level stuff. All right, cool. Have a good one. I will see you next time. Thank you.